worth more because it's super freaking hard to get.
Well, you can also consider going to out of country to take your classes.
You think that's a good alternative?
Many people are out of state already. Many people are going out of state to finish the first 2 years of a community college because I think Arizona and some other states do not have the same issues that we have.
Most of the states' tuition right now, like the UC system, for theirs is about 25% less.
Yeah, but I'm more worried
not
about
surprised.
I'll pay if I get the classes I want, right? Can't wait.
I heard in Texas
a year and a half to
it
get
costs
a
like
class.
$130 a unit at a community college. I heard California is like one of the cheapest places for community
But in
colleges.
Texas, you can go hog hunting and make money and pay for your tuition. But wait, you need to get a $1,500 setup to go hog hunting to begin with. So maybe it will take a while to recap all your spending.
Takes about 2.5 weeks. I have a buddy that did it.
Hog hunting.
You have hog hunting at some props?
Coming soon.
Don't tempt him, he will.
What most people don't understand is, hog hunting is actually protecting a lot of indigenous species throughout the range of the wild hogs because they're destroying the habitats of just about everything. Everywhere they go, the ranchers don't want them, the farmers don't want them, even the animal activists don't want them because they eat everything.
Yeah.
There's nothing left for the indigenous species anymore.
Wait, so there's just wild hogs running around?
Oh, just look it up. Wild hog, as a pest. Basically, they started in Texas, I think. It's a southern state, and they have been moving up, very rapidly. Yeah.
I didn't know that. That's pretty cool. You got roaming bacon.
Yeah, exactly. That's what I thought.
Yeah, we are talking about like 800 pounds of bacon with tusks in front of it.
The World of Warcraft bacon.
I would call that pretty deadly.
Bacon.
Yeah, bacon with tusks, is a little different. All right. So let's go ahead and finish up the topic for extension 2 today, so that next time we can talk about sockets programming, or we can think about the test, the exam, because we need some kind of assessment in this class, and I'm still kind of thinking about how to do that assessment. We'll go ahead and finish up the extension 2 root reader, because we're getting to the root directory. So we'll go ahead and get started with the basic document. And what I will also do is to set up the files and folders. So we'll go ahead and make some copies from last week's, our lecture on Monday. So let's go to today's folder. And today is a leap day, very interesting. I watched the musical called Pirates of Penzance just over the weekend, so that's why the leap day is kind of particularly interesting to me. Have you guys watched that musical? No?
Yeah, let's
It's a really old show. It's called Pirates
I just remember the song.
of Penzance. Okay, I think my spelling is wrong, but Google can fix it. Oh, no, I got it right. Cool. Yeah, the Pirates of Penzance. It's a musical, and it was originally produced in the late 1800s. It's interesting because the company who produced the play was a local company. It's based in Sacramento and Davis, and the performance was in Davis in the Veteran Center. And all those people, in this particular company, they're all, people like you and I. They're not professional performers. They all have day jobs, and they only do this as a hobby. It's really quite interesting. If you have a chance to watch it, just go to YouTube. I think there's a movie too of the same name. Okay. To extension 2. All right, and I have to go set up the files first. So we'll go ahead and copy some files from the previous folder, or the folder of the previous
So were you
class.
saying that Pirates of Penzance has something to do with
Yeah, yes, it
There
does.
is a connection.
Yeah.
The connection is, okay, so I know I'm going to use up class time here. In the Pirates of Penzance, so there's this young fellow. I guess, when the play was made, 21 was actually not that young at the time. Maybe just, maybe it's equivalent to about 30 years, 30 years old, at this point. So anyway, there's this guy, 21 years old with his nanny, and he is in the Pirates. Okay, he's one of the Pirates. And it opens up and go like, okay, I'm 21 years old, now I can leave, the Pirates and actually move on with my life. And it was because of a mistake. The guy's parents told the nanny to sign him up as an apprentice, as a pilot. The nanny heard it wrong and decided to sign him up for apprenticeship with the Pirates. So the Pirates, basically owned him for the first 21 years because that's the contract. Okay, for the first 21 birthdays, you will be an apprentice, for us. So when he was 21, he said, okay, I'm done here, and then he left the Pirates and then met one of the daughters of the major general at the time, and fell in love, and then and decided that I would become law enforcement and I'll catch the Pirates instead. So the Pirates heard about this and then came back and say, you're not quite done with us yet, but I'm 21. Yeah, but the contract says 21 birthdays. And guess what? The guy was born on the 29th of February. So he's only about 5 1/4 at the time. So the Pirates said, you still have to, you're still a part of us. And the essence of the story was, the guy was, I think he's, if you watch the show, he's kind of like the original Wimpy Kid. Because he is just basically saying, okay, it is my duty to blah 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 blah. So everything is a duty thing. So it's interesting, it's and the songs are very interesting too. Some of the songs are really quite interesting. Yeah. So now we have to go back to maybe 1 week earlier. There we go. Okay, so this is the file that we are looking at, and what I will do today is I will start from the very beginning to locate, to get to the part that we need in order to start today's discussion. So it's kind of like a quick run through of all the things that we have talked about so far. Now, since I cannot remember the offsets, I will have to do the same thing that you normally have to do, is to look up, the super block, and then from there you have to look up the block size, okay, or the log of the block size. And then we have to locate the block group descriptor table, which is right after the one block after the block containing the super block. And then from there, we'll go to the inode table. And then from the inode table, we'll locate the entry for the root directory. And then from there, we'll locate the data block or data blocks, depending on how many we need, for the root directory. And then from there, we'll learn about how to parse the entries inside the root directory. So that's what we're going to do today. All right, so the first thing we have to do is to find out what is the block size, which is at offset 24.
Oh, do you have
or
space for the
1/8.
video?
Hmm?
You have space for the video, so it doesn't get cut off?
Is there
Oh,
space?
I got enough space.
Okay.
I think I found out why it was out of space, so quickly. See, right now it has 11 gigabytes. 11 gigabytes. I removed some of the files using the GUI, the file manager, and when I do it outside of the live environment, when I do it outside, it doesn't do any backup. In other words, there's no trash can. When I remove a file, it is gone. I mean, it's completely gone. But I did it a few times, inside the live environment, where it would just move the file from the folder into the trash can. So it's still sitting there, using up, disk space. So that's why it was filling up so quickly, whereas, it really should not be filling up nearly as quickly. So I think that was the only reason. All right. So now we can use hexdump and use -c so I can display byte by byte, and the file is extension to test1.bin. Okay. And I forgot one thing. I forgot to type it through less so I can page up and page down. And also search for items. This is really neat for searching, for a particular pattern too. All right. So what we want to do is to locate the beginning of the super block we already know the superblock is starting at 1024 in decimal, which is 400 in hexadecimal. So this is the beginning of the superblock. Inside the superblock at offset 24, this is a byte offset. We have the log block size, and 24 is 1/8 in hexadecimal. So we are looking at these 4 bytes. But because this is little endian, we are actually just looking at the value of 2. Okay, because this 2 here is the least significant byte, this is the second least significant byte, this is the second most significant byte, and this is the most significant byte. So these 4 bytes actually only specifies a value of 2. But the way it specifies the block size is it's specifying how many times you have to left shift the number 1024. 1024 left shift twice is 4096. So that becomes our actual block size, 4 kilobytes. Are we doing okay so far? This should be kind of like boring because we have talked about this at least 4 times. All right, so now that we know what the block size is, the inode table per group and all of this stuff here, are useful too. So it's the magic number, but I'm gonna skip all that stuff, so that we can get to the content of today's class as quickly as possible. All right. So now we have to locate the first block, or the first block after the block containing the superblock. In this case, this is the beginning, because we have a block size of 4K, and the superblock is only 1K. So the entire first block, the first 4096 bytes in the partition, they're all used up, quote unquote, for the superblock. So the second block, or block 1, actually starts at offset 1000 or 100 in hexadecimal. This is the beginning of our block descriptor table. So now we will switch our notes here to go to the block descriptor table. Right there. And this describes what each entry is saying. What each entry has is a 32-byte thing. And within the 32 bytes, we have these constructs. We are only dealing with the first block group. I think the root directory is guaranteed to be in the first block group. In fact, it's the second entry of all the inodes. And the second entry of all the inodes is always in the first block group. And so this is the first entry is what we're looking for. In other words, these 32 bytes are the ones that we have to focus on. Are we doing okay so far?
Is this the same file that you've given us to work on?
Yes.
Okay, because I thought, yeah.
It's not?
No.
It's not EX2-1.
Okay.
This is
Yeah.
the one he created.
Yeah,
Oh,
this
I
is
can post it.
This is different,
Okay.
because the one you've given us is, I know the block size is 1024.
Okay.
Oh, that's okay, it's fine. I just wanted to not blow
Well,
my
I do
brain.
want your program to be more flexible, so that it can deal with different
It
sizes.
does, it does. I just wanted a sanity check that I wasn't
Oh, okay.
completely crazy, so.
I think you got this one by actually using a whole hard drive. There was some difference, something like it has the NVR as well. There was some difference between.
Well, they're different for sure. But
Yeah.
but
But it's not
I
just
just
the-
had a moment of panic thinking, wait a minute, am I crazy?
Yeah, block group size is different too.
Yes.
Okay, I'm just gonna post this one too. I'm gonna post it right now.
It'd be
so
nice to
that
have another one, yeah, so we can.
you can check your program, against, another test case.
Precisely, yes.
I created it because you have directions on here how to create it.
Yep, that's a good exercise too, how to create one. It becomes handy for other things too. I mean, it's not just for this class. Every time you want to create, because this allows you to really do some experiments with stuff it doesn't run into any danger of
Right.
hurting your actual files. So we'll go ahead and add it as a resource. So we'll link to that extension to test file. And we'll go ahead and upload the file. Oh. Choose file, and we'll go to today's folder. That's where I put the zip file. Link to it. ext2 test1 bin.zip.
Is there a reason why you zipped it and you didn't tar.bz it?
Because some people want to use it in Windows, and zip works better in Windows. I mean, this program can run in Windows because all we are doing is dealing with a normal file using seek and read. So as long as Windows has lseek and read implemented as well,
It does?
you know, it should. I mean, you know, that's a fairly common operation. I mean, I cannot imagine why Windows would not have lseek and read implemented. Can anyone confirm one way or another? I think Windows has it. I mean, you know, it's a very, very common low-level file operation that should be supported by any operating system.
Does it have standard in, standard out, and standard error?
In Windows,
Yeah.
yeah, if you use GCC to compile a program, you know, those those file descriptors should be pre-initialized.
Oh, okay.
Yeah. Yeah, you just have to make sure that you're using a command line program and not a GUI program, so that you have all these tools.
So this right here you have highlighted, that's our block descriptor table.
That's the first. That's the descript. That's the end. That's the entry of the first block group. Yes, it's a descriptor for the first block group. So we'll now go back into the notes here and interpret these 32 bytes. The bitmaps are useful if you want to check the sanity of your file system. But for our purposes, you know, it's not really used. So we'll go ahead and just go straight to the inode table, which is at offset 8. It has 4 bytes. So offset 8 is here, and it has 4 bytes. So what this is telling me is it is block 4, which is actually the 5th block because we come from 0. So this is block 4, and now we have to locate block 4 to locate the inode table of this block for this particular block group. Are we doing okay so far with the hunting so far? Okay. We already know that each block is 400 in size, so we have to multiply 4 by 400 in hexadecimal, and that will give you 1000 in hexadecimal. Yeah, because 4 times 4 is 16. 16 is 10. Oh no, it's. I think I missed one more 0. It's 1000 in hexadecimal. Just to be sure, let's just double check. Where's my calculator? Don't have one. All right, we'll use a command line calculator in that case. Or we can use GDB. GDB is really handy as a calculator too. Have I shown you guys this trick?
I think so.
Print /x means I'm using hexadecimal output. So we want to multiply 400, which is
1024.
Block size.
a block size.
Yeah, block size.
Is that right? No, that's wrong.
bigger there.
No, our block size in this
It's
one
4096. We can just specify 4096,
I think.
which is 1000, 1 followed by 3 zeros in hexadecimal.
I thought your block size in this example was 1024.
No, not the one that we are talking about in the class.
The other one.
Oh, okay.
And then we have to multiply that by 4 because the block ID is 4. Okay, so that gives me an offset of 4000 in hexadecimal. So now we can go back to our hex dump, which is over here, and go to there. So this would be, let's see, we have 128 bytes per inode structure, and each line is 16 bytes. So we need, yep, go ahead.
I thought you said it was 400.
Oh, that's right, okay. Pointing to the wrong place. Okay. So 128 bytes is 80, so these would be the first entry of the inode table. This would be the second entry of the inode table. Now which one do we want?
That one.
That one, because the first one does not correspond to the root directory. It is, it has the same kind of structure. It's an inode table, which means it has its own blocks. The 15 entry table thing. It has its own, first data block, second data block, and so on. So what do you think those data blocks, quote unquote data blocks, are pointing to? Bad blocks. Okay, that's what the first entry is it's basically using the same kind of structure that we have talked about for the data blocks, but instead of actually pointing to data blocks corresponding to a file or a folder, is pointing to blocks that are known to be bad, so that the file system knows what to avoid and not to use. Okay, which I think is a pretty neat way of doing things, because there's no need to reinvent the wheel just to remember where the bad blocks are located. All right, so this is what we're looking at, and now we have to move on and look at the inode table. Particularly, we want to look at the inode structure, because now we are accessing individual inode structures. The root inode structure, you should first double check the imode and make sure that the imode tells you that it is an entry that is a directory. Okay. If it is a directory, you should see this particular bit pattern. 4000 means that if you do a bit mask on the most significant 2 bits of the 16-bit entry, you should still get a 4, and that's the first 2 bytes. So we'll take a look at the first 2 bytes. Okay. These are our first 2 bytes, and we do see a 4 here as the most significant hexadecimal digit. So that means we're good. Okay, this is a directory. Are there any questions so far?
I don't quite understand the bit masking there.
The bit masking?
I mean, I understand bit masking, but I don't understand how it's used right there.
Okay, let's go back and look at the values. When you look at these values, which is basically telling you what kind of file we are dealing with here. If you look at 1, 2, 4, 6, 8, A, and C, they require only 2 bits to represent. Okay, 1000 in hexadecimal is 0001, 0000, and then another 8 zeros after that. 2 is 0010. Okay, so when you get all the way down to C, it is 1100, 0000. So that means okay, so that means we have to mask it with the upper 4 bits. Sorry, so I was wrong, not the upper 2 bits, but the upper 4 bits. The most significant 4 bits are important to tell you what kind of file it is. So to double check this is actually a directory, what you need to do is, okay, let's say I shouldn't use I, because let's use M for the mode, okay? So let's say M is our mode, the 16-bit that you're reading in. So what you want to do is to use a bitwise AND with the bit mask. In this case, it will be F000. In other words, after this operation, if you look at the bitwise AND operation, all the bits that we don't care, all of these other bits, will all be turned into zeros.
Right.
Only the 4 bits that we care will still be retained. So that means when after this bit mask operation, you should compare that to 0x4000, because that tells you that it is a directory.
What's wrong with just taking M and ANDing it with 0x4000?
The only problem with that is C000 also has the same bit set. Because this is 4, right?
But does it matter? I thought we were only looking that it's just that 1 bit. If it
Nope.
said it's a directory.
No, we have to look at
set.
4 bits here, because 1100 means something that's completely different. If the bit pattern is 1100, it matches C000, which means the inode represents a socket instead of a directory.
Okay.
Okay?
Yeah.
Yep.
I assumed that the ones that use multiple bits to represent them were. I assumed that meant, for instance, that a block device was a directory and a character device. Conceptually, according to the specification, that's not the case. They just needed to overlap bits.
Say it again?
I assumed that they were using multiple. Since a block-defined device uses the same bits as masking a directory and a character device, I was kind of assuming that they were just saying, "Oh, we're going to call a block device a directory character device." So that's not the case then.
I don't think that's the case. I think the original intention was really just use the bits in a bit map manner. So you only look at individual bits, but then they found out that quickly they found out they ran out of combinations, and also you cannot have a character device that is also a FIFO, so there's no need to use the bitmap method. You can just use the sequential number method instead. So that's why we see kind of like a mess here, because some of these kind of looks like a bitmap method, and others are not. So, but basically, if you do the proper bit mask here and compare that to the proper value, then you can correctly identify what kind of a file you're dealing with. But regardless, we know this is a folder, a directory, because of this 4. Okay, so I don't even have to do any bit mask operations because 4 is 4. Okay. Are there any questions?
So, okay, so never mind. I got the question.
Okay. So that's basically just a sanity check to make sure that we are in fact dealing with the root directory, because if you look at the first entry, it has a 0 here. A 0 here is not corresponding to any of the file formats, and that's because it is special. It is not really a file. It is really just representing all the bad blocks. So right now, we have a good sanity check, and everything seems to be good. All right. Yep.
So FIFO, it's a pipe, right?
A FIFO is a named pipe.
Named pipe.
Yep. The pipe that you normally use using the vertical bar symbol,
Yeah.
they're unnamed, which means they are not actually persistent. If you shut down your system, or in fact if you shut down the programs that are using that pipe, the pipe goes away. When you have a named pipe, then it is persistent. So after you reboot the system, the named pipe will still be there. Good question. All right, so this is good. Our sanity check works out, and so the next thing we have to do is to find out how many blocks the root directory is using. Now isize, I mistakenly told someone that isize is what you need to read, but that's actually not the case, because isize is only indicating the size of the file in bytes in revision 1 or later revisions, only for regular files. And the root directory is not a regular file. A directory is not a regular file. If you look up the mode, a regular file has its own entry. 8000 means it's a regular file. So the root directory is not a regular file, so that's why you cannot just use that isize to determine the number of bytes that you have to read. Instead, you will have to use iblocks to determine how many blocks or how many data blocks you have to read, because here it says iblocks is a 32-bit value representing the total number of blocks reserved to contain the data of this inode. Now the keyword here is reserved, which means these many blocks are actually reserved. It doesn't mean that it is using all the reserved blocks. The difference is there because when you're reserving something, it is always helpful not to only reserve one more than what is needed. Okay, those of you who have taken data structure will probably remember this. When you have elastic arrays, an array that can grow in size,
Like
a lot of times you double it. Okay, every time you need something bigger, you double the size instead of just making it one entry larger, because that way you're pre-allocating stuff and you don't have to access the file system again and again just to allocate another block, another block, another block. I'm not quite sure how Linux does the reservation, but in any case, this tells you how many blocks are currently reserved for this file. The file may not have to use all the data blocks at this point. Okay. Are there any questions about this part?
Yeah, when you refer to a dynamic array, well, that's not what I meant, but the way you said it, were you talking about a vector?
In our data structure class here, students are required to implement what they call an elastic array, where the size of the array, is dynamic. You can actually increase the size of the array as you use the array. But in that case, you have two choices. Okay, if you want to increase it, let's say the original size of the array is 32 entries, and now you're requesting, I want 33 entries for this array. You can just do a new operation or do whatever memory allocation you need to only allocate for 33 entries. Okay, But you also have the option and say, well, instead of just reserving 33 entries, I'll just bump it up to 64 entries. So if you do it with the 64 entries, that means you can allocate 32 more items, and there's nothing it has to do with memory. Now, what is that saving you? There's a certain advantage of doing something like this. What is the advantage?
Less time copying to the new array.
Less time copying, and there's another advantage to it, which is actually even more, in a certain way, more important. You will have less memory fragmentation. Okay, how many people know what is malloc or new, depending on C or C++? The concept of dynamically allocated memory. The problem with dynamically allocated memory is you can end up with memory fragmentation. In other words, you can have your memory. Okay, let's say this line here represents your memory. You can allocate and deallocate it in a certain way so that your allocated portion would just be kind of like spaced out evenly throughout the entire memory space. So the solid blocks here that I drew, are the ones that are allocated. The white space is not allocated. You can see that I've only used a very small portion of the total space. But if the next malloc or new requires requests a space about this big, I cannot. There's no block big enough for the next malloc, even though in theory there's enough free memory. So if you malloc and free, or if you use C++ new and delete all the time, and things are all of different sizes, you can end up with a situation like this.
So what does it do? It gives you a new heap?
The heap can probably bump up in size too. I'm not sure whether the heap size is dynamic itself or not, but typically that's a system operation. You can ask the kernel and say, can I increase the size of the heap or something? But sometimes you just run out. But this is a waste of space. So even if you can just ask the system to allocate more space, it is still inefficient. It's a very inefficient way of using memory. This problem does not exist in Java, because in Java it has dynamic memory management. That's garbage collection. That's it. The name is garbage collection. Because in Java, you don't really have pointers. Okay? In C, you have pointers, but in Java, you don't have pointers. It's called a reference. A reference is interesting because it's a two-way thing. A pointer is a one-way thing, but a reference is a two-way thing. So that means if the system decides to move things around, it can come back and tell you or your program, your reference, that the location of this thing has changed. So now you can have a garbage collector to come in here and collect all the garbage. Garbage means this chunk here, this chunk here, this chunk here. So the garbage collector would compact everything. Everything that is in use will be bundled up at the beginning, and you end up with a large empty space after that. And that's why in Java programs, sometimes it will run really fast, and then at a certain point it will just stop and do nothing. It's because it's doing garbage collection. Because garbage collection is something that has to, for the most part, you have to stop a lot of the system activities in order to do garbage collection.
So what are we supposed to do in C for that? We have to design our own garbage collector?
In
To
C,
prevent fragmentation?
there are, to prevent fragmentation, there are several ways to do it. One is to avoid using malloc and free. If you already know that you can have up to, let's say, 1024 of a particular structures of this size, do your own maintenance. Do your own, basically malloc and free, so that you will just be recycling things within a big array. So from that perspective, you are statically allocated, a certain chunk of memory only for that kind of structure. But that's okay, because you already know in the worst case, you will only need 1024 of those things, so you just pre-allocate everything. You can do your own memory management too. You can do that also in C++. You can override the new operator for specific types, for specific classes. So that allows you to do your own memory management, but only for specific classes.
I have one question on overloading operators. Can you overload anything? Can anything be an operator?
Only operators that are recognized by the system are operators they can override.
Okay.
They can overload. All right, so getting back to here, so we wanted to go to offset 28 in decimal, which is 1C in hexadecimal. So 1C is the hexadecimal, and we are looking at the second entry here. So 1C plus 80 is 9C, and we are looking at this number here. It's using it's reserving 8 data blocks for the root directory. Are we kind of doing okay here? Does it make sense? I think so. I mean, unless I'm counting it incorrectly. Each line has 16 entries. So this is line entry 24. This is line entry 28. So we are at the right place. It is reserving 8 data blocks. Okay, so once we know it is reserving 8 data blocks, we want to know where the data blocks are located. So we have to go to the block part of an inode structure to find that out, which is at offset 40. Offset 40 is 28 in hexadecimal, so that would be 28 is here. This is the ID of our first data block. The other data blocks are all zeros, which means they have not been allocated yet. So this is contradictory to what I just said. You know, the reserve amount doesn't mean that they are all reserved, or they don't have actual data blocks reserved yet, because these entries are all zeros. Are we doing okay so far? So we only have one data block actually, allocated to this root directory. Yep.
So it almost sounds like the reserved data blocks would just be maybe so that it doesn't fill up the block group with kind of promises that it can't actually deliver on. Do you have any idea why there would be that contradiction?
The description doesn't really say anything about that. This is the description of blocks. The maximum number of blocks per inode will vary based on the block size selected of the file system. We know that part already. A 32-bit value representing the total number of blocks reserved to contain the data of this inode, regardless of if these blocks are used or not. So I'm assuming that there are blocks allocated, but because they're not used, they do not get reflected in the array. But then who's keeping track of where those blocks are? The block numbers of these reserved blocks are contained in the I block array. So we should be seeing 8 entries in the I block array in this case, and yet we are not.
How do you know you're not, just because they're 0?
Yep.
Because they're zeros.
How do you know they're not reserved?
Can't reserve block 0.
Okay, I block, and okay, right here, a value of 0 in this array effectively terminates it with no further block being defined. All the remaining entries of the array should still be set to 0. So that means we only have one block allocated. But yet, according to I blocks, there are 8 blocks reserved, unless I do my calculations incorrectly. But I don't think I did my calculation incorrectly, because there's no entry here that has a 0, 1 in it. So, yep.
For purposes of this assignment, can we assume that the root directory is only going to use one data block, or does our program need to be able to handle multiple data blocks?
You can still, in the end, figure out how many data blocks it's using, because you have one block that is non-zero, but the next one has a null terminator basically. So you already know that you only have one single data block in this case.
Right, but does our program need to be able to handle a root directory that has more than one data block?
No. I think one data block is enough for me. It's already complex enough as it is, so this is fine. All right, so we have 24 here as the ID of the data block of the root directory.
Oh, here I was worried about indirection. We only need one data block.
Yep, only one. Yeah, the root directory has to be fairly large, like 12 times 4K.
Right.
It has to be
It's
larger
indirection.
than that in order to get into the indirect block. Yeah. And that means you have to have either very, very long file names or a lot of files in the root directory itself in order to require that many bytes. Okay, So we are looking at 240000. 24 in hexadecimal is 36 in decimal, because the 2 is 2 times 16, and then the 4 is just 4. 2 times 16 is 32. 32 plus 4 is 36. So now I can go back to my GDB and do some calculations. We have 36 times the block size, which is 4096 bytes. So now we have to go to offset 24000 in the partition to find our first data block. So switching back to you. Oops, okay. Here's my dump right here. So we are quite conveniently going there because everything else are zeros. This is our root directory, and potentially you have up to 4096 bytes of this entire block. So when you're reading it in, you really have to read in the whole thing, because the structure terminates by itself, but then you have to traverse the linked list to find out where it terminates. So when you're reading it in, just read in the whole block. It's only 4096 bytes. I'm not going to give you a block size that is insanely large. So just allocate for the block size, read in the entire block, and then parse it. It's far more tedious to do it entry by entry. I mean, you can do it entry by entry, but it's actually even more tedious that way. So now the question is, how do we interpret these particular bytes to find out that we have a folder called lost and found and another folder called testdir? That's our question. Now we have to go back to the web page again, and we go to section 4. Section 4 talks about the directory structure, and in our case it is a linked list directory. We talked about how to find out whether it's a linked list or not. It's one of the bits of the Inode structure that tells you whether it's a linked list or indexed directory format. In this case, it is a linked list. So we'll go ahead and find out how do we parse this these entries here. A directory file is a linked list of directory entry structures. Each structure contains the file, the name of the entry, the inode associated with the data of this entry, and distance within the directory file to the next entry. Okay, how many people know what is a linked list? Okay, this is where the data structure class comes in handy, because a linked list is one of the simplest data structure that is introduced in that class. All right, but we'll talk about how to deal with this. So whatever entry you have in it, they're all broken up into these entries here. The first 4 entries have fixed sizes. In other words, the first one is the inode, which is always 4 bytes. The second one is the length of the record. It is always 2 bytes. The third one is the name length. It is always 1 byte. And the next one is the file type. It is also only 1 byte. And the last one is the only one that can have a variable length, which is the name. Okay. All right. So the other parts tells you how to interpret all these numbers.
Should we read this into a structure?
No, you don't want to read this into a structure. You should probably just read this. You should just use an offset to a pointer to interpret different parts of it. Yeah. Yep.
Why isn't the name null terminated?
Why isn't the name null terminated?
He said they have the length instead of just...
So that you can use a null character as a part of the name? I don't know. I mean, yep.
Well, it may be null terminated. Does it say anywhere that it's not null terminated, or are you just assuming that because it specifies the name length?
We'll get to that part. Yeah. When we get to that part, we'll deal with it. Okay. The first one is the inode, which is the first 4 bytes of an entry. When we get here, the first 4 bytes of the entry is this part here. So that means the inode of this particular file is inode 2 in the entire system. Inode 2 of the entire system in this really small file system would still belong to block group 0, the first block group. So we'll still use the same inode table that we used to find the root directory to find this one here. Okay. The next 2 bytes is the record length. In other words, this is telling you the record length is 12 bytes. So the next question is Is it 12 bytes from the beginning or 12 bytes from here? The answer is,
From there.
I think it's 12 bytes from the beginning.
Oh, okay. Yeah.
Because it's the length of the entire record. In fact, if you go here, it's a 16-bit unsigned displacement to the next directory from the start of the current directory entry. The current directory entry starts with the inode, so it's from the very beginning of the entire entry. Okay? So that means knowing that the length of this entire record is 12 bytes, I know where to find the next entry already. The next entry starts here. And it has the same inode number.
That's suspicious.
This is awfully suspicious, yes. Let me think about it. If that's not the one, it's even more suspicious. Then we'll have a really kind of weird inode number. So we'll keep parsing this one. Okay. So I still think that the first interpretation is correct. In other words, the next entry is here. After the record length, we have the name length is an 8-bit unsigned number indicating how many bytes of characters are contained in the name. This value should never be larger than record length minus 8. If the directory entry name is updated and cannot fit in the existing directory entry, the entry may have to be relocated in a new directory entry of sufficient size and possibly stored in a new data block. Okay, so let's find out what that means. In our case, the name length is 01. Now, I know exactly what is going on now. There are hidden files. One of the hidden files is called dot, and one of the hidden files is called dot dot. Okay, so let's see whether it is really dot and dot dot. Okay, we'll look at the actual file name. Okay, the next entry is the file type. It's an 8-bit number value used to indicate the file type. So now we have these different file types here, and I'm guessing that this is a file type 2. Sure enough, it is a file type 2. It's a directory. So what we know at this point is the inode number is 2. We know where to find the next record, which is here, which seems really weird because it's another entry of the same folder which points to the same inode, which means it is actually the same thing that what we are looking at in this case. The next item that we were looking at was the 1, which is the file name only has one single character. And then the next entry is the file type, which is a 2, which means we're dealing with a directory in this case. Okay. And then after that, we have the actual name. This is the name. This is the hexadecimal representation of the ASCII code of representing the character, 2E. So what exactly is 2E? I'll give you guys one guess.
No.
It's a dot.
Yeah, it's a dot.
It's a dot, and that's why it doesn't show.
It's printed.
It's right there.
It's that dot over there.
That's
Okay, but we'll confirm that. Okay, I don't trust myself, so we'll say man ASCII, and then look for 2E, and 2E in hexadecimal. Sure enough, it's the dot. Okay, so are we doing okay so far? Interpreting each entry of the directory. Oh, a dot. Do you remember what a dot means in this class?
Correct directory.
The current directory. Yep. So that's why it is pointing to the same entry. Okay. Well, no, it doesn't explain why it's pointing to the same entry as the next entry. Okay, so we'll deal with that too. Okay. All right. So we are almost there. Getting back to the hex dump here. Okay. So this is my only character. The other 3 bytes are basically not used in this case. Yep.
I'm assuming it's kind of a dynamic allocation scheme. Why allocate 1 when you could allocate a few extra so you don't have to relocate the entry?
I think it's 4-byte aligned. I think it's a 4-byte aligned thing, so that you always want to start a new entry at a 4-byte aligned address. Okay, this is our second entry. The second entry, is pointing to inode 2. Okay, the same entry. The offset to the next entry is also 12 bytes. So that means we have to count 12 bytes from this byte here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the next entry is starting here. 02 means this file has 2 characters. The file name has 2 characters. 02 here means the file type is also a directory. Now, would you expect anything different from a 02? If the first entry has a 02 and this is pointing to the same inode, they should both be a directory. And the file name is 2e2e. I know the length because of this. I know the ASCII codes are 2e2e. What do you think that looks like? Dot dot. So that means from the perspective of the root directory, the current directory is a dot, the parent directory is dot dot. But since the root directory is the very first or the first directory of the entire system, it has no parent directory. So the parent directory is itself. Is that okay? In fact, I can illustrate it pretty easily in a command line interface. I go to the root directory, ls, it doesn't show the dot and the dot dot, but if I use ls-a, it shows it. You can see the dot here, you can just see the dot dot over here. If I say cd dot, it remains here. If I say cd dot dot, it's also still here. Yep.
What is dot dot deb? What is dot dot deb?
Dot dot deb. Well, it looks like I don't know. Let's see. What is the file
maybe
size?
Debian files or something.
I probably accidentally created this file here, using a wrong file name. It's probably a package file. Okay, now here's another utility program in Linux that is really super duper handy. It has a very unassuming name, just called file. It's the name of the command. But if you use it on anything, it will tell you what kind of file we're dealing with, regardless of the extension. You can mess up the extension really, really badly, and it actually looks into the content of the file, compare the content to signatures and patterns of known file types, and then give it the best guess of what kind of file it is. Not always accurate, but for the most part, it is pretty good. Sometimes it will misidentify, like Microsoft Word, the new docx file will be, sometimes it's reported as a zip file, but it is actually correct. Because a docx file is actually a zip file with XML files inside the zip file, and that's why it is reported as a zip file. Yeah, it's really, really handy. A file as a utility program is very handy for identifying what kind of file you're dealing with.
Why doesn't Windows have something like that?
Because Windows is Windows. All right, so moving on to the third entry. The third entry starts here. It's 0B, and this means these 4 bytes represent the inode number of this particular entry. The next entry is 20 bytes from here. In decimal is 20 bytes because 14 in hexadecimal is 20 in decimal. And you can see the length of all the entries are always multiples of 4. Okay, so that kind of confirms my suspicion that it is a 4-byte aligned kind of thing, which makes sense. Okay, it makes sense that it's always 4-byte aligned because when you access memory, if you're always dealing with 4-byte aligned addresses, it's actually more efficient. All right, the next one tells you the length of the file name is 10 bytes because A in hexadecimal is 10 in decimal. This is also a directory because it has a 02 for the code. At this time, the 10 bytes as the file name is interpreted because these are all printable characters and they're not dots. Right? I mean, the other two folders, are printable characters. They're actual dots, but they got intermixed with the non-printable characters, which are also represented by dots when you use the hexdump program, and that's why they were kind of buried and not it's not obvious. But this one is pretty obvious. It's lost plus found.
But just before you move on, okay, the 0A in the line above is 0A02, and the 0A was
file type?
Oh, yes, gotcha. Okay, thank you.
So in this case, the type is also a directory.
Thank you.
Sure. So the next entry starts here. The inode number is C, which is 12. And yep, it is correct.
So what does that inode number represent again?
This is the actual, when you look up the inode table, this tells you, where to find the inode representing the next, the current entry. And okay, the file name is not associated with an inode.
Yeah.
The file name is associated with the directory. So you can actually, if you want to, you can have a hard link. What a hard link is multiple directory having entries like these pointing to exactly the same inode. That's a hard link, which means when you do something to that file, then it is multiple directory can see the changes at the same time because they're really referring to the same physical file. So after that, we have a D4 as our
Record length?
record length, and this one is rather long. Okay, D4 is a rather long record name, and then we have 0f as the actual file type. I can't remember what 0f means. It's a file type, so let's go. Nope, not one. Where is it? It's not one of the file types that are defined. Okay, that means I might.
Did you get the right starting point?
That's what I'm thinking too. Okay, let's check it again. Okay, this 0C means we have to count 12 bytes from here. So we have 1, 2, 3. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the beginning of the next entry, and we interpreted this one correctly. And it's 1, 4 from here, so we have to count 20 bytes from this byte here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this is the beginning of the next entry.
Is that going to be tester? We're to tester right now, right?
Yes, it should be corresponding to test dir. And what I'm not getting is this is the inode. Okay, as an inode, it makes sense. The next one is a record length, and it's telling me the record length is really quite long. It's 0fd4 as the record length. So we'll take it the way it is right now. So we'll just kind of take it the way it is right now.
It does make sense considering the number of zeros afterwards. Maybe it's just padding out the rest of the table.
I think it's just padding it. In other words, it's also keeping count on. So when you have to create a new entry, it would just shrink this one and then create additional entries. The length of the file is only 7. The length of the file. The length of the name of the file is only 7, which matches test dir here. The file type is 02, which means it's a directory. And these 7 bytes are basically the ASCII code of testdir. And then the rest of it are not used. Because the file name is the very last thing that you have to deal with inside an entry in the directory. And the length is only 7. Even though we have reserved fd4 bytes for this one. So now so what we're going to do is we'll do some calculations here, and I'm thinking if you look at this number, which is fd4, don't you think that's really awfully close to the end of the entire data block?
Yeah.
Because the size of a data block is 1000 in hexadecimal, and f something is pretty close to the end. So I'm thinking that if you use the address of this byte and you add fd4 to it, you will get 0fff. Okay, let's do some mental calculations here. No calculators. This location is what? Okay, we are at offset 2, 0 here. and this one is 12 bytes from that location, so we are looking at 2C. This location is 2C. What happens when you add 2C to D4? Yeah, 2C plus D4.
Well, I'm at 0FF. So
You get 100 in hexadecimal. And then you round that up, that carry gets to here, and it becomes 1000 in hexadecimal. It makes sense. It goes all the way to the end of this entire block.
Is the file name also Little Indian, meaning that it reads backward, or does it read the way from left to right?
The file name?
It's reading left to right. If you just do the translation.
Okay.
Yeah, because it's not, we're not combining the bytes to become a 16 or 32-bit integer. So we are still dealing with bytes by, in this case, we're dealing with the bytes as themselves.
Okay.
Because one byte is representing one character, so there's no need to understand little endian versus big endian.
Okay.
Now, when you have a file system that uses Unicode, then it's a different issue because a Unicode requires more than 8 bits to represent one character, so you have to deal with little endian again in that case. But since this is all UTF-8, it's just 1 byte per character. All right. So do we know how to interpret the entries in a directory at this point? Just manually? Yep.
So if we had a root directory that spanned multiple blocks, then it probably we would have an entry that would get us like to the end of the first block at some point. It wouldn't, one entry wouldn't cross between blocks, right?
That's a good question. I do not know the answer. Yep.
Also, I'm noticing that there isn't a name for the root directory here. Does that just assume because this is the beginning, then it's named root? Or
There's no name for.
There's no slash in there.
But these are things that this folder contains.
Oh.
So the thing itself has no name.
Okay. And just by convention, we use slash for it.
Well, you have to start with something. So so the first entry of the entire file system, you cannot look it up by name because what are you looking it up from? If this is the very first entry of the directory system, so that's why the root directory has a slash as a symbol, but that's really just a name that we give it when we have to specify a file in order to specify the path. We could have chosen another character to mean the root directory if we wanted to, but it's just conventional to use the slash in this case. That's a good question. Any other questions? I think we have enough pieces to do the homework now. I mean, if you look through the entire homework assignment, we are really down to what we have just talked about for the past half hour was how to analyze the root inode. Now that we can locate the root inode, it's time to analyze it. We have to do a sanity check, make sure the inode is a directory. The root directory is indexed or it is linear linked. In this case, it is linearly linked. Loading the root directory, you can track it down. Just use. In this case, the I size really doesn't matter. You have to use the I block. You have to use the I block to tell you how many blocks you have to read. It's all contained in one single block, so don't worry too much about that part.
And if I block is 4, then are we really looking at the literal 4th block of memory? From
Yeah.
the beginning?
Yep, that's what we did actually. The block ID is 4, so that means the offset of that block from the beginning of the partition is 4 times the size of each block, which is 4096
And
in
it
this
is from
case.
the beginning of the partition, not from some arbitrary point after. I guess
It's
that
from-
makes sense, of course, because we already were block aligned when we.
Yep, it's from the beginning of the partition.
Gotcha.
Yep. Yep.
I'm trying to think about it, and I still don't quite understand why what the C is, the 0C for it's the node we were saying, and how they all started with 0C, and then there was one that started with 0B for I think it's the.
That's the inode number of that entry. In other words, okay, let's go back to the dump here.
I hope it's not a.
Okay, you're talking about this 0B here.
Yeah.
That's the inode index. This is the index into the inode structure of lost and found in the inode table.
Is that something that's hard to go back and explain? I think I'm just not making.
That's kind of like okay. If you look at a folder or the content of a directory as a phone book, this is kind of like a unique ID of a person. Okay, something that is truly unique to a person. The file name itself, which is these bytes here, is just a name, of that particular person. So what we're doing here is we are listing, who is in this directory. This is the name that we know that the entry for, it's just a literal, it's just a name. But to the file system, this is the location, this is the index of the inode that is actually representing that directory. In other words, if you are to find out, what is the content of lost and found, or what is the content of testdir, what entries are in testdir itself, in this case, you will have to track down inode 12 in the inode table, and then track down its own blocks in order to find out, what entries do we have in testdir. Yep.
So you can have many things named lost and found. There's only one thing with inode 12.
It's the other way around. You can have multiple things that have inode index 12, but they can have different names.
Oh, that's like we did with the dot and the dot dot.
Within the same directory, you can only have one entry of each name. The name of every entry inside the same directory has to be unique. But they can all point to the same thing if you want to use hard links to do that. Is that making any sense? Okay. Yep.
Going back to the I block, when it was like I block 4, that's the offset, right? So we're actually looking at the 5th block. Is that correct? From the beginning of the partition?
No, blocks are zero oriented. So we are looking at the 5th block, but it is called block 4.
Got it. Okay, just want to check.
In your calculation, you only use the number 4.
Right, because then you're saying, okay, here's all those 4 blocks, and go right after that. That's where you started the 5th block.
Now, what you have to be careful about is the inode number itself, the inode ID, is actually 1 oriented and not 0 oriented.
Okay.
So what this means is, we are actually looking at
The
index
second
1, which is the second inode, which makes sense because that's really the root directory.
Right.
Okay. So in this case, we are looking at 0A. It's number 11, but it's index 10 in this case, and the next one is actually index 11. So by recursing into this, if you have a recursive function and go to this block, go to this inode entry and do the same thing, then you will have a way to recursively go into every single folder and find out the content of every single folder, starting with the root. Any questions? Yeah. No questions? Okay, let's go back to the homework assignment. Make sure that we can answer all the questions. For each entry of the root directory, print the following. The inode number, do we know how to find the inode number? Yeah. Okay. And you just need to print that number itself. You don't have to worry about being 1 oriented or 0 oriented. Just whatever that number is, print it out.
Do you want it 0 filled?
No 0 filled.
Okay.
The file name is ABCDE, so you have to print out the file name of the file. This one gets a little bit tricky because it's not guaranteed to be null terminated.
You know the length, and they're all characters. So
Yeah.
just printed little loop of characters should be okay.
You can use a loop to do it. You can also use printf has some really cool features. When you use %s to print out a string, you can also specify the length of the string in the parameters. So if anyone wants to do it like that, using printf, a built-in feature of printf to do it, that's good too. If not, you can just use put char and just print it character by character until you run out of length. Yep.
So it's not guaranteed to be null terminated, but
Nope, it's not
chances are if
guaranteed.
we do run into null terminator, then it's probably the end of the string anyway.
In order to make it not null terminated, it's pretty easy. All you have to do is to make a file name that is that has the number of characters of the file name is a multiple of 4. Okay, let's go back to the dump and I'll explain why. If you look at a tester is not a good one, but lost and found has 10 characters. These 2 bytes are only there for padding purposes. So if the file name use up 2 more characters, it would not have any padding anymore.
So you'd want
then-
to check the length of it, but if you do run into a null, then it's probably the end. That's what I meant is you want to go for at least the length of the. Or you
Just
wanna
go for the length. Only use the length to indicate how long the file name is. Do not use a null terminator.
Well, what I mean is you would want to make sure that you go at least, or you want to make sure you go the length.
Exactly
But
the
if
length.
you do run into a null, that's probably, before you get to the end of the length. Does that mean that it's going to be the end of the file name?
Let me try something like this.
Does that make sense?
Yeah, I know what you're saying, but what I want to do is to create a file name that has a null character in it. Let me see if I can do that. Okay, so we'll go ahead and touch. Well, first of all, we'll do something that should be able to do. We should be able to do it. We go to the ASCII table. We'll go specify. Okay, let's create a file name. Just call it Z. Okay, Z has an octal number of 172, so we'll use that 172. Touch 172. And it just created 0172. I was trying to escape and get me and see if I can specify the file name using the escape character.
Backticks around it.
Backticks?
That forces the backslash to be an escape, I think.
No, the backslash itself is escape, but it's only escaping the 0. So it's not using it to specify a character in octal number. This is a bash issue. If you were to use the open, if you use open and give it a file name that has a null character or something in it, that becomes that's the question. Can you create a file like that using just open? Because if your file name can contain the null character, then you cannot use a null terminator at all. When you see a null character, you have to keep going. Is that making any sense?
Yeah. Just thinking, what are the chances,
So that means we can't use printf, because if you use printf with the length, it's going to stop at the first occurrence of the null terminator or the length.
Right.
So we'd have to use the length.
Right.
Also, you can't use %s with printf then.
Well, let's go ahead and spend the rest of the class creating a file name using a null character as a part of it. Yeah, that's a good exercise. I mean, I really think these are good exercises.
But is it going to make a difference as far as what prints on your screen? I mean,
It doesn't make any difference, but it does make a difference. If you have additional characters after the null character, the question is, will that also be displayed? Do you see what I mean?
yeah.
Okay, so we'll go ahead and create a file name with that. Okay, so we'll just say null file name. And of course, I cannot remember how to use open, so we'll say man to open. Okay. Copy and paste.
So you might get
Yeah, it looks
extra
ugly.
line. So what do you edit?
Ah. Okay, there we go. And we want to use open. Oh, we have a problem here because this is a null terminated string itself, which means I cannot contain the null character when I specify a file name to create.
Have you checked the spec on the file name in ext2 to make sure that it doesn't say anything about null? Because if it does, mentioned that, it might clarify the issue.
Prohibit the null character.
Okay, Unix-like operating system take a different approach and only prohibit the null character and the path separator from appearing in file names. So there you have it.
So we can use printf then. Percent %s.
Yes. So the file name cannot no, because it can still, if the file name is a multiple of 4, then you are not guaranteed to have any padding characters after the file name,
Oh,
which
yeah,
means
Right, but we won't encounter a null character in the
In the middle,
of our
that is
file.
correct. You won't
use
have-
printf with the length.
Yeah,
Correct.
passing string length as an argument to printf.
correct. Yes, you can do that. Yep.
Are you sure that the behavior isn't to, in that case, extend by 4 bytes to make sure that it is null terminated? Because it could conceivably do that.
Yes, it can conceivably do that.
What about like the ASCII bell character or something?
The bell character is Control G. You can try it.
It says it's legal.
Also, I believe ASCII
Yeah.
also.
Anything other than the slash, I'm not even sure the slash itself is permission denied. Okay, so it cannot I cannot touch
Do it. To do it.
Yeah, because it's not treating it as a file. It's definitely escaping it. Okay, we want to try the bell character. So yeah, you can do it. The first one is the one.
But it doesn't bell when you type ls.
Well, we don't have the
It's gonna be funny if it actually does.
Okay, first of all, we want to see whether echo does it. Is it?
A lot of terminals have it disabled.
Well, I might have a volume control issue here, so will double check. What is my default output? It is here. And we're playing back the system sound. Output devices. I'm not. Okay, let's go to YouTube and see if I can actually play sound in this case.
Play soils redefined.
And we'll look for Pirates of Penzance.
That song was done in Mass Effect 2. Did anybody see that?
What one?
This
Monsters! Area pirate caravan!
Okay, fine, it works. Okay, so the bell character doesn't ring the bell character.
You even have it disabled in your terminal.
Yeah, that's what I'm looking next. Okay. Nope, cannot be shortcuts. Has to be either general or appearance.
Google?
Help!
Might be something in an RC file that you can customize.
Yeah, it's not echoing the bell. But that would be pretty funny. If you have a file name that has a bell character, and every time you do an ls, it goes ding.
Let's make a file name that's really long with a lot of bell characters.
Yeah. Okay, now we have another question. Since this is Linux programming class, in the end, people will end up with this problem. How do we delete that file? Okay, so we can try several things. We can say remove ? Oh, that actually works. So it's not really the bell character. It's actually a question mark.
It may get redirected to that then.
So it's.
But it still
okay.
didn't echo the bell.
Okay, how about this? How about Control H, which is a backspace character, right? It translates it into the question mark too. So if I say remove question mark, it also removes that file.
What if you name one the bell character and one the backslash? Then how does it represent that when you ls it?
How about this? So a file name that starts with normal characters, and it just turns into question mark. Oh man.
That translates to.
Oh wait! But this is interesting. The question mark works only because it's a wildcard character. That's why it works. Okay, Okay, let me explain what I meant by that. Okay, so I can be doing touch 1, touch 2, touch 3, touch bell. Oops, yeah. Touch backspace. Oops, no, that's delete. Okay, never mind. It's good enough. Okay, so we'll go ahead and do a RM, question mark. In that case, it removes every single file that is only 1 character long. So that means if I want to delete only one of those, I would have to use the actual name. So remove, Control G will remove just that file. So you can, in fact, so the file name actually is using the bell character as a part of the file name, but when it is displayed, it's only displayed as a question mark, because I think it has to do with the ls command itself not wanting to print unprintable characters as a part of a file name.
What would happen though if you had a file name named the bell character and a file name named the backslash character, and then you LS'd? Would it show 2 question marks?
Yeah, it did.
Yes.
Oh, it did?
There's one in the beginning and one at the end.
Oh, okay, thanks.
So Control G, and then maybe backspace.
Well, no, I'm sorry. I meant 2 different files. Oh, that's what you're doing. Okay.
Yeah, it's a single file with 2 unprintable characters.
Oh, but I meant 2 files. But I guess that.
Oh, okay.
Would it show you just 2 separate files, both named question mark? Okay.
Yeah, I think so. I think we just.
Really?
Yeah, it did.
Huh.
Yep. So you have 1 question
Okay,
mark here and 1 question mark here. Now this part it's only because it is sorted. The delete character actually has an ASCII code of larger than everybody else, all the printable characters, and that's why that's the one at the end. And Control G is smaller than all the other file names that I have created up to this point, and that's why it's all the way to the beginning. To confirm that, if I say RM Control V, the delete character, only the last one should go away. The first one should still be there. So we'll take a look. That's really the case.
So, is there any way to distinguish between those 2 files, since they both have the same name, or that's just how it displays them?
You can, if you want to. Okay, let's do that again. I know that we are just having a little bit of a obsession here. But when you do a tap, it actually shows you the actual the file name here. So the first file is a Control G, which is the bell character, and the last one is a Control question mark, which is the delete key on your keyboard.
What did you do to get that printout?
Tap. If you just say ls and then tap, double tap, the first tab will try to do autocomplete, but since I did not specify any parts of a file name, the autocomplete cannot work. But when I use the second tab, it will show all the files with the same beginning. But since I specified nothing for the beginning, it shows all the files completely.
I'll have to try it, because when I do tap at home, it makes the bell sound. So we have to see
No,
if it'll-
in that case, it makes the bell sound because there's nothing.
Oh yeah?
I think so.
No, it's still...
Yeah, mine does that too, I think.
It
bells.
also makes a tab if there's ambiguity.
Oh, okay.
So if you have a beginning with file name, then
So I must have the sound turned off, or something, because otherwise I should be hearing the bell sound too.
Yeah.
Yeah, that must be what's going on.
Yeah. In this case, I'm not, seeing anything because it's just turned off. It's not generating any system sound. Otherwise, I should have heard something here. I've seen something here. Well, maybe not. Anyway, so do you guys feel comfortable with the homework assignment?
Yeah.
What if I give you 1 week to finish it?
It's fun.
Let's do it.
You just procrastinate for 6 days and then get it done on the 7th day, right?
I love this
Hey,
stuff.
I had a flat tire, and I don't know where I got a flat tire from. So can I get your name and phone number in case I need it? In case I miss one. It's just
Go to Harbor Freight and get a patch kit. I know how to patch tires.
No, I think
And
that,
an area code too, because I don't really.
I think Les Schwab fixes flat tires for free.
Yeah, they're nice. Oh, I already got it fixed. It's just I don't know where the nail came from.
Hello.
Hi, how are you?
I'm good. Sorry we are a little bit late today.
That's okay.
Thanks, man. You got it. Have a great week.